Hello and welcome to Linear Regression Module 3, Deep Dive. We'll be looking in detail at advanced methods in linear regression. Dr. Mark Williamson, the DaCCoTA project for the University of North Dakota. So, let's get started here. This is the third module in the series of linear regression. Previously, in the first two modules, we covered a broad overview of it, looked at more detail into the methods of regression, as well as running through some examples. Now here, what we're going to be doing is looking at more advanced methods. In particular, the three I've highlighted to show today is Generalized Linear Mixed Models, Longitudinal Analysis, and Structural Equation Modeling. So just review briefly before we jump in. We learned in our previous modules that linear regression is the technique of modeling the relationship between a response variable and one or more predictor variables. You can think of all the different types of regressions in some general ways. I broke it down by one structure. You can have simple regression with one x, one y, multiple regression, multiple x's and one y, and even multivariate where you have multiple x's and multiple y's. Different regressions will depend on characteristics of predictor variables. You might have polynomial terms, fixed or random terms, nested terms, etc. There's also characteristics of response variables that make for different regressions. Like normal regression, also known as Gaussian, there's logistic and Poisson that all deal with different sort of types of data. And then there's also many other considerations, such as time series, possibly truncated data, all sorts of nuances that might require a different approach in regression. But regression is such a broad topic that almost anything you'd like to do can be covered. Another thing we talked about is the process of like what's going on with regression is essentially the process of ordinary least squares, where you're trying to essentially minimize your equation of best fit so that all your actual observations are as close to that fit as possible. We'll see here that ordinary least squares are not the only way to go about things, but that is typically the starting point. We also learned that you really need to consider assumptions in model fit, that there are different assumptions for different types of regression. You need to fit those to have reliable outcomes for your models. And then, finally, just to summarize everything, there's lots of ways to run a regression. And we'll see today that with the more advanced ways, can tackle a lot of more advanced problems. And so here, just once again, kind of the visual 1-2 punch for what's going on is you have observations shown in these green dots. Your regression line is that model, that equation of your best fit, and then of course it's never perfect, so you always have some sort of error. All right, so the topics we'll be diving in today, as I said, generalized linear mixed models, and I'll be using SAS software for that with SAS Studio. We'll then look at longitudinal analysis, where I'll be using the omnipresent R. And finally, we'll jump over to structural equation modeling, where I'll showcase it with Stata. So let's dive in. We'll start with generalized linear mixed models. So what is a generalized linear mixed model, also known as a GLMM? Well, it's a combination of a generalized linear model and a linear mixed model, which isn't a particularly helpful description. So let's break down the parts. So the generalized part of this means that it accommodates for non-normal distributions. For example, like it can run logistic and Poisson regression, both non-normal regressions. Then the mixed part of it, it allows for random effects. So a linear model only allows for fixed effects, so say like treatment categories, but then a mixed model allows for both fixed, like that, and random, like say, like block or something like that. It allows for the mixing of the two of them. So that's what we mean by a generalized linear mixed model. So there are some really key differences I want to parse out as well between a GLMM and a linear model. First of all is the method of estimation. So for a linear model, we talked about ordinary least squares. However, for a generalized linear mixed model, typically you would use maximum likelihood, which essentially what's happening is it iteratively maximizes the likelihood of parameters given data. What that kind of means under the hood is a lot more computationally expensive things than ordinary least squares. So that's why ordinary least squares was kind of the first method developed, or maximum likelihood. Now that we have pretty regular variable powerful computing access, it's not that hard to do now. There's also other types of estimation, but maximum likelihood is the most common for GLMMs. Of course, then another key difference is distributions. So for linear models, you can only use normal distributions. That's why if your data isn't normally distributed, you have to transform it or try something else. But that goes away. We've already seen that with our examples in Module 2 by looking at logistic Poisson regression, which have either a binary distribution or a Poisson distribution, respectively. So there's a wide range of distributions that can be used, from count data to ordinal data and so forth. And then to deal with that, so there's this thing called a model scale. So generalized linear mixed models will link expected values to a model scale with a certain kind of link function. So to kind of understand that, is that you have data on one scale, that your observations, your measurements, but then you want a scale for your model for it to run properly, and then pull it back to the data scale. So it's better to kind of visualize this. So there's three main links. There's identity, log, and logit link. So identity link, I mean, nothing happens, it's identity, so there's no difference between the data and the model scale. But say we look at the log link, on the data scale, it's count data, so it doesn't go below 0, and so the link accounts for that. The logit link is bounded by 0 and 1, so it accounts for that as well. So like log link, this is good for count data like Poisson distributions, negative binomial distributions, exponential distributions, and so forth. Logit link is good for things like binary distributions, binomial distributions, beta distributions. And so like let's do a quick example here to flesh out like why, a little bit more why links matter. So say you're doing, you have a y variable that's binary 0 and 1. If you try to do a linear regression, you get this line, this best estimate line that goes above 1 and below 0, which is impossible for the data you have. Your data is either 0 or 1, and really a lot of times what you're doing is you're modeling the probability of a 0 or 1, so it doesn't make sense to have negative or above 1 probability. But a logistic regression, which uses this S-curve logit link, constrains it so that your model ends up staying within the bounds of the data, that it never goes below 0 and never goes above 1. So that's stuff on the model scale. Finally, let's talk about random effects. So again, random effects in a model are contrasted with fixed effects. Fixed effects are typically the things, some sort of category that you're interested in. Say you have some sort of outcome of a disease, and you have different treatments. Those are your fixed effects. You're interested in those. You think they affect your outcomes. But then a random effect might be something like the hospital. Maybe you have several hospitals you try your experiment on. Now a lot of times random effects, while you might be interested in variations between categories, random effects are usually things you do actually care about, but you know that there's variation there, so you want to account for it. Like maybe different hospitals will have different outcomes regardless of treatment, and you want to kind of partition that out. And so that's what adding random effects can do. And you can have different levels of it. You can have both random intercepts and random slopes. So let's walk through an example with some visualization. So say you have a single level model here, and say that you're looking at your y variable is, say, like score for like a test, and your x variable is like number of hours, studied. And you expect that, the more hours you do of studying, the higher your score is going to be. That would be just a single level model. But say you had a random effect, like say you looked at different courses, physics, math, social studies, history, etc. You could have a random intercepts model where your random effect is your different classes, your different courses, and you can allow each of those groups, those courses, to have a different intercept, that is, a different starting point. You see the slopes are all the same, so the relationship between the score and the amounts of others studying is the same, but their starting point is different. You can imagine that could make a lot of sense to do that. Maybe some courses like up here, pretty basic information, so if you don't study at all, you still do pretty well, but obviously you do better if you study. Whereas harder courses, maybe less intuitive courses, like say maybe mathematics, if you don't study at all, you're going to do very poorly. But as long as you study enough, you're going to do okay. So that's random intercept model. Now you could also imagine doing random slopes as well. So this is a random intercept and slopes model. You can imagine different patterns going out where each of these classes has different intercept, a different starting point, and a different slope, a different relationship between score and studying. You can imagine them fanning out, kind of clustering at the end, or no real relationship like that. And again, this might make a lot of sense. Say you have, a course like a really difficult course where you're going to do very poorly if you don't study, but it takes a lot of studying to do well because it's such difficult material, where some material, it doesn't take a lot of studying to do very well. So, kind of in a nutshell, the take-home point with generalized linear mixed models is they account for a wide range of different data requirements, including different distributions, having fixed and random effects, and the like. We'll be using SAS to look at generalized mixed models and coding. So the primary procedure I use is proc-glimix. So for the basic random intercepts, you'd start by, you need to have a class function for anything that are categorical, say like your treatment and your random effect. And then you'd have your model that has your kind of model with your fixed effects. So your response, the thing you're interested in, your y variable as a function of treatment. And then you need to set up your random effect with the random statement. And this is typically how you do it with intercepts. You have intercept as your random, and then a slash, and then whatever your random effect is, so subject equals whatever variable your random effect is, hospital, block, I don't know, course, whatever is your random effect. Now, typically, you'd be doing this with a categorical treatment. Of course, if it's continuous, like say, score and time studied, you would just leave treatment out of the class effect. Now, and also it turns out in a simplified form, if say with your random, you just put your statement random and then whatever variable without doing this whole intercept slash subject equal, this is essentially comparable. They'll do the same thing. Though I do suggest using this format just to get used to it so you know what you're doing. So turning to a little more complicated, so if you have nested effects in your data, like for example, if you're looking at student outcomes from teaching style and you're looking at different schools within a state, well, we knew that this is hierarchical, that schools are nested in states. So you would have a random effect like this where you have state, and then to show the nesting, you do school is nested in state. Sometimes you're actually looking at just random effects. Maybe you want to look at the amount of you're doing an exploratory data analysis for like a pilot study, and you want to see how much variation different levels of treatment, or sorry, not different levels of analysis are. you might do something like this, where maybe you have 3 different random effects, tree, branch, and leaf, and you model your response as a function of actually nothing, and then you have your random statement here. So there's tree, branch, which is nested in tree, leaf, which is nested in branch and tree. And then you can look at the various, how much variation was in each level. And that might be interesting because, like, say there's a lot of variation in tree, then maybe you want to measure more trees in your sampling. Or maybe there's a lot of variation in leaves, so you want more leaves on tree. So it could help negotiate resource limitation when setting up experiments. Finally, we can have the randomized slope as well. Do that sort of like the random intercepts only. You know, your random statement as a class, and then instead of just intercept and then subject random, you include whatever your treatment is into your random intercept. We will look at 4 examples in SAS of GLMMs, multicenter, NPK, RC, and wings. Multicenter RC are available from here, and then NPK and wings are from elsewhere. All right, here I am in SAS Studio. We'll walk through 4 examples. We'll start with a basic GLMM with a categorical treatment. So I have my data here that I will create and print. So the idea here is we're looking at 15 different centers, so that's our random effect. 2 different treatment groups, that's our fixed effect. And then our response variable is going to be the number of side effects out of the total group, so proportion of side effects. So if we want to look at our data a little bit, I'm going to create a new variable called proportion of side effects so we can take a look at that. And then let's run a couple plots to take a look at the differences. So here's the proportion of side effects. So it goes from 0 to 1 in between the 2 groups. And we can see, yeah, it looks like there might be a difference, possibly. But then here is our random effects at 15 different centers. And we can see that the proportion of side effects varies quite widely, both in sort of the mean, central tendency, as well as the amount of variation. So then to run this, we will run a proc glimix. We see here group is a class. And this is just a glimix without any random effects. I always like to start without random effects to see how a basic model would be. Fixed effects only. So we run this. Main idea is this is a binomial. And since we actually set this up as side effect over n, it knows that we're doing a binomial response distribution. If we used this new variable we had here, we would have had to set our own distribution. So just a heads up here. So let's go down. So fit statistics. One thing to look at. 1 is the ideal. If it's above 2, you might want to redress it. So there might be a reason this might be over dispersed. But then the main thing is here, it looks like test for fixed effects, F value is significantly large, that it's lower than 0.05. So it looks like group is significant. So it looks like, kind of interpreting the parameter estimates, looks like group B is sort of set as this default, so group A is lower. So that looks like group A has a lower proportion of side effects. And that group would be like a treatment group. So now let's add in our center as a class variable and then as a random effect here. See what that does. So we go down. We see the fit statistics actually do a lot better, so it's a better fit. And this is our covariance, so that random effects, it looks like it's not 0, or 0 would be theoretically there's absolutely no effect of center. Anything above that, obviously the level is going to be kind of different, but looks like there seems to be a moderate effect, and group remains significant even accounting for that. So in summary, it looks like it was a good idea to add centers or a random effect, and either way it was significant. So now let's run this one more time here. So we're using this is going to be the same sort of setup. I just wanted to show you here that this random intercept / subject equal center is going to give you the same output as this. And then we're going to do ls means so we can print that out, and then we'll do a plot from there. So again, same sort of output, least squared means, and then here is our output. Yeah, so it looks like group A has lower proportion of side effects. Okay, and then we'll move on to example 2. So now we're going to do a basic genome with multiple treatments. It's a little more complicated. Here's our data. We're using the card setup instead of the data lines. So it's a little different here. So this is data from NPK experiment, nitrogen, phosphorus, and potassium. So it looks at a yield of a certain plant and whether or not nitrogen, phosphorus, or potassium were added. And then by block, this is our random effect. So again, let's just do some look at our data here. And yield looks pretty normally distributed, so I think we're just going to keep it as is. We don't need to use a different distribution. We're going to sort and look at just different variations. Looks like nitrogen. Looks like no nitrogen. Having nitrogen might improve yield. Doesn't look like phosphorus does anything. Looks like adding potassium might actually decrease yield. So that's good exploration to figure out what we're expecting. And then let's just take a look at block. And it looks like, yeah, it looks like there's a fair amount of variation in block that we might want to account for. So we're going to start out again. N, P, and K are each of our classes, and we're going to model it, yield as a function of these, as well as the interaction. Once again, I have no fixed effects here. I like to just run, or sorry, no random effects. I like to run fixed effects only just to take a look. Pretty high chi-squared, so we can definitely improve our model fit. Residuals look okay. Looking down here at fixed effects, looks like nitrogen alone is significant. Phosphorus alone is not. Potassium alone is not, and none of the other interactions is significant. So that's what we found here. But now if we add in our block as a random effect, let's do that. We'll also print out our least squared means. Runs. Chi-squared it's better. I mean, definitely looks like we could still do better on our model fit here. Then here's covariance. So this is our block and our residual. So it looks like block actually has quite a bit of, covers quite a bit of the variability in our data. And when we look at our fixed effects, we see nitrogen is still significant. But interesting, now potassium, after accounting for the random effects of block, is now significant, which is good to know that, yeah, it really mattered that we added our random effect in here. And so if we just plot these here, we can see here that, yeah, once again, higher yields for nitrogen, but lower yields for potassium, positive plots. Okay, continuing on, we're going to look at generalized model with, now we're going to include random slopes as well as our intercept. So we're going to once again do data here. This is how to do that. And so then this is the idea of, I think, data for like stability of pharmaceuticals. So this is a Y variable, our iteration. So batch is a random effect. And then we're not going to use this categorical month, but month is our continuous X variable. So let's just do histogram of our Y variable, and it seems like it's Might be normally distributed, but we should check this. It definitely looks like it's more of a count, maybe a count variable or something similar, or some sort of rate variable. And then, so we'll also take a look at here, plots here. So this looks like this is month, so time period, and our y variable, and it looks like there might be a negative correlation. And if we separate that out by batch, there definitely looks like there's differences between batches. So there might be a reason to have both intercept and different slopes. So I'm going to start this out here by just doing 3 different Glimmix models using only fixed effects. So we're just going to have month, y as a function of month, and we're going to try a couple different distributions to see which one might have the best fit. So this is the Gaussian or normal distribution. Looks like month is significant. Chi-squared degrees of freedom, pretty high. Residuals, okay, maybe not great. Let's go on to Poisson. Ooh, really looks like it's under-dispersed. And residuals are okay. Again, it's significant. Go to a negative binomial. Again, pretty low. And residuals are okay. So I think based on that, we're just going to keep it with Gaussian. You could definitely play around with this, find a better fit, but just for this example, I think we'll keep it as close enough to normal distributed that we'll do it. Then let's run a plot Glimmix. Now let's add. First of all, let's just do random intercepts. So random int, so this is just a shortening for intercept. Y is a function of month. And then our random is batch. And then this S is for solution. So we run this. Looks like batch has based on residual. It doesn't have a lot, but does account for some of the randomness. And it looks like month is significant. Residuals, like I said, kind of a bit of an art of it. Don't look too egregious. But now let's try this with both random intercept and random slope by adding month to the random statement. And chi-square is a little high, but actually not too terribly bad. And we look at, looks like some of this batch definitely has kind of the most variation. And if we look at our residuals here, it kind of looks like a little bit of a shotgun blast, so this might not be the best. So you might, if I was actually doing this for a real analysis, I probably would work a little around more, but let's just say that this is good for now. We have our solutions, and see now what we see here is that month is significant, but then we have for each batch, so we have 3 different categories of our random variable. For each batch, we have an estimate for their intercept as well as their slope against month. And you can actually, what I did here is I made plots. We're going to look at plots for both this and this model. We're actually going to add lines for the different plots, the different random effects categories. So I just did this manually by pulling out the information from the results. So if we see here, this is the dotted line is sort of the overall model fit, but then this is the random intercept. We can see batch 3 started out higher, but they have all the same slope. Or like batch 1 is in the middle, batch 2 is the lowest. But if we can have random slopes and intercepts, we see the slopes will be different. So it looks like the y variable drops fastest for batch 2. That it starts about the same as 1, but drops a lot faster. Where batch 1 and 3 start a little bit differently, but have about the same slope, kind of merging closer to each other by the end of it. So that's pretty interesting results. So then finally, we'll look at a generalized linear mixed model with nested effects. And so instead of creating my own data, I'm going to actually load it in here. It's a Wings data set. This will be available along with the code where this is posted. So let's take a look at the Wings. So this is wing size for different flies. So there's individual, there's a block, there's a site, class, whether they're urban, rural, there's pot, month. There's a lot of data here. The thing we're interested in is in wing size. So that will be our y variable. Let's just take a look at histogram, and maybe close enough to normally distributed to just go with it for now. So let's look at across sex, a possible fixed effect, and then block, a possible random effect. We see that, it looks like wing size is larger, tends to be larger in females across, and it seems to be really relatively the same across these different classes, rural, suburban, and urban, as well as looks like the wing size tends to be bigger in block 2 than block 1. So that's important to know. So our response is wing size. We really don't want to use an individual a day. Possible fixed effects are block, class, and sex, and then possible random effects are site and month. So we're going to kind of build this up as we go. So we're going to sort, and let's just start with a very simple data set, seen as if wing size is different across sex, just with a normal distribution. Let's take a look here. Sex is, very significant, but there might be under dispersal here, and residuals don't tell us too much because this is sort of that binary category. So let's add some more stuff. Let's build it up. Now let's add seen as wing as a function of sex, but then let's add site and pot as random effects, where pot is nested in the site. Okay, a lot going on here. Looks like these do have a little bit, account for a bit of a randomness. We see that site definitely accounts for a little more than pot. So that's important to know. Say if we would do this again, I'd have more sites than more pots per site. And again, though it looks like sex is highly significant. Let's keep going. Let's now look at wing size as a function of class and sex and their interaction. Again, keeping site and pot as 2 nested random effects. Keep going here. Again, now they still are random effects, still counting for some of the randomness. And now it looks like class doesn't really have an effect or the interaction, but sex is still significant. And then finally, let's do the biggest one of all. We have class, sex, and block. And random effect is site, pot per site, and then month. So let's try all these. And here, a lot of times block is a random effect. Here it's actually a fixed effect, just a heads up. So it looks like now in this situation, pot has the most variability, has the most randomness, then site, then month. So that might be important. And then fixed effects looks like sex is important. Block is important, which is not surprising what we saw from our box plots. And then their interaction actually is significant as well as interaction between class and block. So a lot going on here. We'll just take a look at a couple outcomes here. So here is block and class. So it looks like across class, block 2 is higher wing size. And again, it's for sex and block. The females in block 2 have the largest wing size, but looks like in males, they're different. They're different by sex. So females have higher in block 1, block 2 versus block 1. Same with males, but then males have overall smaller than. So even the males in block 1, they're pretty much on par with males on block 2. All right, with that, that is our example in SAS. All right, here we are at an assessment. 4 questions here. Suggest pausing, working these out on your own before continuing on. All right, for question 1, we're asked how to set it up. So you would have treatment and hospital as class because they are categorical. And you want to model your medical outcome as a function of treatment, and then make sure to add hospital as a random effect. So for 2, matching the links. So Poisson and negative binary, those are count, so you want that log link. Binary data needs a logit link because that's bounded by 0 and 1, and then normal data just has the identity link, so nothing changes. Random effects. So throughout this, it seems like school, block, and site will probably be random effects. They look like different measurements of different locations that you're not necessarily interested in, but you want to account for. And then here's some outcomes of a Glimix. So for the fixed effects, this is down here. Solvent looks like it's significant. And then with the random effects that's found here, looks like colony is a random effect. Does look like it does have some effect on the model. It's above 0. And then the fit of the model, Pearson chi-squared over the degrees of freedom, is very close to 1, so it's actually a very good fit. So now let's swim over to our next approach, longitudinal analysis. So to describe this, it's data that is especially because it's a multi-level data in which that there's multiple measurements of the same thing. So time, we're cared about longitude over time, typically. So time is nested actually within individual observations or participants. And one participant has multiple time events of measurements. And so that the response variable and predictor variable are typically measured several times at each of those responses, time periods. And the point of this is to characterize change. So a lot of times you look at spaghetti plots to explore this kind of data. You have some sort of outcome on the y and then time, and each time period that outcome was measured. And different individuals obviously have different trajectories, but you're kind of trying to look at characterizing change over time. And now what makes longitude analysis a little bit special is, like regression, you need to link your predictors to response, but you also, because it's over time, need to account for correlational structure repeated measurements. Because the outcome measured from this individual at time 1 is related to it at time 2 because of the same individual. Like if you measured my body mass index now and in a week, they're going to be highly correlated because I'm the same person. So the simplest case of longitude analysis that you might analyze would be using something like repeated measures ANOVA, where you maybe have 2 different, like a control and a treatment, and then over a couple of time periods, and see if there's a difference across treatment and possibly time. Now, more sophisticated ways to approach this would be linear mixed effects models or generalized estimated equations, both of which we'll take a look at. Because these are relatively complicated, you might think we'll continue to use SAS, but you are wrong. We're going to be using R, because where we're going, we don't need SAS. So here's generalized kind of schemas of formats for it in R. So you could do for repeated measures ANOVA, it'd be something simply like that, where this is your equation, but then you add your error term like this, where in longitude data, your random effect, essentially your individual participants, because they're measured across time. You want to kind of nest your data to show that, you know, each of your treatments is nested by your individuals. And then you could build a more complex equation because you have to account for correlation between your different individual time points for the individuals, but you can set your correlation structure differently. There's that's why I have these different sort of options. You won't add all four, you add one of these, and there's more, but these are kind of the basic ones. And we'll see these go. This one has compound structure. This is essentially unstructured, where you actually can set unequal variances. This is another form, AR1, and then this is the same one, but then now the variances can be unequal. If you're moving to linear mixed effects, you can use this LMER function, and same sort of whatever your setup is, y is a function of, like, say, maybe treatment and time. Maybe you have another categorical variable. And then this is to have the random intercepts. It's in parentheses 1, and then whatever, you know, your random effects like participants. To do intercept and slope, same sort of thing, but instead of 1, you add a time here. So you have the times, the slope of the time can vary, as well as the intercept where it starts. Then for generalized estimating equations, you have just GLM. Also just generally a generalized linear model. You start with this, you know, y by your treatment, and whatever distribution you need, because generalized estimating equations don't assume normality. But then you're going to compare with this GE. This is the actual estimating equation. So we compare this to your GLM. Then you add your random statement, and then your different correlation structures. Can be independence, which is sort of the naive version, or exchangeable, and you can set your scale to be fixed or not, and we'll kind of look at these more in detail. It's kind of the general. So for our actual examples, we'll be using this phlegbitis, using repeated measures ANOVA. This is based on this lesson here. Then we'll be looking at beat the blues, respiratory and epilepsy data, using both a linear mixed effects model and then generalized estimating equations. And these are all based on examples from a handful of statistical analysis using our book. I've switched this over here to RStudio. So let's look at the first example. This is a phlebitis. So it's essentially inflammation of a vein. So we're going to look if there's a difference across time, across different categories. So we're going to need ggplot2 to plot, and then this NLME. These are different packages, so you'll need to install them if you don't already have them installed, and then call them with the library function. So I'm going to take a look at it here. So here's our data. Let's pull this up a little bit. This is our data. So essentially you're looking at different animals and then different treatments and then time. And then the Y is essentially looking at inflammation. So the difference in temperature between the year that had the treatment and the year that didn't. And let's take a look at spaghetti plot. See what we're talking about here. So this is, so first of all, this is just looking at differences across time, but then if we want to look across different individuals, these are all different individuals of measurements across time to see if there's a difference in inflammation. And then we can also do, maybe we want to look just by treatment, not just individuals. So if you want to do this manually, you can create means and name them, and do all this sort of setup. Follow this here and color it, and you can actually pull this out, and it looks really nice. You can see that looks like for treatment 1, there is a increase over time. For treatment 2 and 3, they kind of look like they're about the same. A little bit different pattern, but overall pretty similar. And then it also turns out you can, instead of doing all this, you can just do an interaction plot. But it isn't nice to know you can do it manually too. It doesn't look as good, but it's a lot quicker. You can see the difference between treatments and time. So what we're trying to model here is this y, this difference in inflammation, as a function of treatment, 1, 2, or 3, and then animal, which is nested in treatment. That's how you show it there. And then time, because we're going across time, and then we also want to look at the interaction treatment in time, and then whatever sort of error. So to the analysis of variance, we're going to do that here. And we're going to make sure treatment and time, they're factored, so R knows as a category. Then our error is also going to be factored. That's our random effect, each individual animal. We're going to run that. And it looks like, both time and the interaction between time and treatment is significant, and treatment is significant. So that's good to know. And then so let's set up that sort of nesting information so we can try these more general equations. And so we're going to try 4 different ones. We saw that kind of in the schema. Same sort of model for each of these. We're going to have treatment and time and their interaction. And this is set up so it knows it's nested. We're going to try this compound symmetry, essentially unstructured symmetry, and then the AR1, AR2, and then both with and without variance is unequal. So we're going to create all 4 of these. And then what we're going to do is we're actually compare them with just ANOVA. That's a way to compare models. Take a look at these. And it looks like, based on, let's look at AICC or AIC, looks like the lower is better. So it looks like this fit AR1 is actually the best. But this, the simplest model, the compound symmetry, is actually not too far off either. So we're just going to run these out just to see what they look like. And it looks like either way, they're pretty similar either way. Treatment was significant, time was significant, and the interaction was significant. So not surprising that we see that. If we were to kind of conclude, it looks like treatment 1 has the biggest difference, and it's completely different from all these other 2, and it increases over time, where these 2 don't necessarily look like they increase over time or are different from each other. So that interaction term is this being different over than this, and then increasing over time. There we go. I'm just going to detach this. So that was using ANOVA. Let's take a look at a linear mixed effects model now. And so if you're starting to think, wait, isn't a linear mixed effects model, haven't we already talked about that? And the answer is yes, because it is a component, or essentially a subsection of generalized linear mixed models. Generalized linear mixed models is a linear mixed effects model, so it has random and fixed effects, but doesn't allow for linear mixed effects don't allow for non-normal distributions. So we see here there's a lot of interplay between models. So we're going to use, we'll need these 2 packages, and then part of this HSAUR has this data set, Beat the Blues. It's looking at a difference in these BDI, it's depression index. So I think the higher it is, the more depression across different times and different treatments. Is traditional treatment or this different kind of treatment called Beat the Blues, and also having length and then possible confounding variable drugs. So let's see here. And so we're going to just do some stuff here just to reformat it a little bit. We actually want to turn it to a long data set. And then we can, after we do that, we can kind of see now that we have it long. So there's the pre-value, but then there's the subject, but then now the BDI is long instead of wide. And it's time across time. So then we'll set layout and just some different formats here. And so we want to try some box plots to explore it. So this first one here is like the BDI across time for like the normal treatment, and this is the beat the blues. So it looks like, you know, they both go down, and the idea is maybe beat the blues is a different kind of treatment. Maybe it does better to reduce BDI. This is a depression index, so once again, lower is better. So then we're going to try a couple of these linear mixed effects models. First of all, let's try a random intercept. So that's where the BDI, these are all the things we think might affect it. And then our subject is going to be our random intercept. And then we'll try another one where we actually have random intercept and slope. So time by subject, that'll create that. So we'll run those, you know, store them as these objects. And then we'll compare the two with ANOVA. And it looks like actually the first model with just random intercept is a better fit. So, or lower AICC, so we'll keep that. So let's take a look at the summary of that. Okay, a lot going on here, but looking at the fixed effects, it looks like whether or not, it looks like time was significant, which means, yeah, things change over time. I think the big thing here is this treatment. Or sorry, so that's the standard error. Sorry, that's not what we're looking at here. Time really didn't have much of an effect. And treatment didn't also seem to have much of an effect, whether or not you were treated user or beat the blues. So let's take a look. And then here's just some estimates of randomized residuals. So this is a fit for it. It's like, okay, this seems to look okay. So as you notice here, there wasn't any p-values, but we can kind of take a look at like the t-values here. It really doesn't look like this is going to be big enough to be significant. Now you can, for whatever reason, LMBER doesn't, on principle, doesn't show p-values. You can use special things to, you know, to actually get them. But I would say based on this size, it's really not going to be significant. Now, before we move on, it's good to bring up a common issue in longitudinal studies, which is missing values. It's not uncommon for you to do a study with, say, participants, and not all of them finish, like they drop out or don't get all the data, you know, at each time point. And different types of missing data have different problems with it. There's three main kinds, which is completely at random missing, or non-ignorable missing, where it's sort of specifically not random. And so you need to keep that in mind, and you might have to correct for that, depending on what type of missing data it is. I'm not going to go into that too much here. We're just good to note. So let's shoot over to example 3. Now we'll start looking at the generalized estimating equation. So we'll use respiratory data, and this will be logistic data. So we'll need to pull in our library. we'll get this. Again, this respiratory data is from that library of HSAUR. So there's a respiratory data at different centers, treatment and placebo, and then whether what their respiratory status was. So we're gonna do some cleaning up the data here. The main thing is we're gonna actually recode, so then we'll have NSTAT as a dummy coding for poor respiratory status. Let's see here. Now that we have it, we can see here that's either a 1 or a 0, good or bad. So we're going to start with a generalized linear model, looking at status as a function. We see here we're going to start with status as a function of center and treatment, sex and baseline, and age. And this is a binomial function, so we'll set the family. But then we want to then also create our generalized estimating equations. So we'll use NSTAT instead here. Otherwise, same setup. Then our ID, so that's our random effect, is going to be our subject. And then our correlation structure, we're going to just try independence. And then we'll do another one, we'll have it as exchangeable. So run those as well. And then we'll take a look at each of these. So all right, so just for our GLM, it's pretty straightforward. Here are our coefficients. And it looks like things like center, treatment, is a they are significant. Same with whether or not your baseline was good in predicting your outcome, as well as age. But then when we go to here, the generalized estimating equation, things are more complicated. So what's actually going on with generalized estimating equation that goes above and beyond the GLM is that your standard errors are going to be off if you don't account for the correlation between, your measurements across time. So what the GE does is actually uses this thing called a sandwich estimator to estimate those. And what you can do is you can tell how well your model is fit by comparing your standard errors of each of these estimates, the naive ones with the robust ones, which is after the sandwich estimator, and then the closer they are together kind of tells you how well the model fit. So for our first one, where we had a independent co-structure, so we see here's this, and they are different. So there might be some evidence that we would want an exchangeable correlation structure. If we go down here, we see actually with this here is the standard error and the robust standard error are actually almost identical, which means it seems like that was the best fit for the model. So there we go. So let's interpret this. What's going on here with the treatment? So since this is a logistic regression that's going on here, this estimate here is actually the log odds of treatment. So whether or not you had treatment, the log odds of having this respiratory status is 1.299. Now log odds aren't particularly helpful. We like odds. So what we're going to do here is, first of all, get the standard error out, set that in there, and then take the exponential of this log odds to get the actual odds, and then use this of the coefficient to get the confidence intervals. So we see now here that we have 3.66 is actual odds, and then that's above 1. So the confidence interval shows that it's indeed significant because it ranges from 1 to 7. So therefore, whether you had the treatment, you're over 3 times more likely to have a good outcome. All right, lastly, let's take a look at another generalized estimating equation. But instead, let's use Poisson data, so our count data. So this is going to be epilepsy data. And once again, you'd use Poisson regression if this wasn't repeated measures. That's all you do. But since it is repeated measures, we want to be more sophisticated. Here's our epilepsy. So we have a treatment, things like placebo or the actual treatment. Base number of seizures, your age, seizure rate. So this is that Poisson, it's a rate, so count, seizure rate, and then over periods, and then the different subjects as a random effect. So doing some data here, this is just kind of formatting the data. I'm not going to go too much through it. Setting up, so we either have this drug pregalbide or the placebo. And let's use some box plots to explore the data. And so this is the number of seizures and then across different periods, whether or not that's difference between the drug and the placebo. And it's hard to tell here. There might be some evidence that it does lower it with the drug, but that remains to be seen. But since we're going to be using a Poisson distribution, which has a log link, it might be better to actually look at this as log transform. So we're going to do that, try some box plots with that there. And so now these are log number of seizures, and that makes it a little more orderly. And, it's still unclear whether or not there's any effect of the drug. I'm not sure if there really is, but we will run through these things. So then, since these actually periods in time aren't actually equal, it's better to actually offset them. So our rate is per time. And that's pretty common in Poisson regression to have an offset. So we're going to start with a generalized linear model to kind of compare to. We're modeling seizure rate as a function of the base rate, your age, and the treatment, so whether placebo or the drug, and then have an offset of like the period length. Well, then we're also going to have 3 different generalized estimated equations. We're going to look at independence, exchangeable, and then with or without fixing the scale. So we'll run those and do some quick summaries here. There's a lot going on here, obviously, so I'll try my best to pull out what's going on. So looks like treatment is in the general linear model, treatment is significant. And typically, this base and age, those aren't typically values that we actually care about. So in this case, we call them confounding factors. We include these because looks like they do make a significant effect on seizures, but we're not actually interested in them. We're only interested in the treatment, but we include those to correct for this relationship that they have to the number of seizures. So then we go to our first estimating equation model. And so we're going to see how well it fits, compare the naive to the robust. And it looks like they, pretty different. So the independent assumption is probably not the best fit. So let's look at the exchangeable with fixing our scale. And between two, it looks like it does better, but there might be room to improve. So if we go here, these look pretty close between the 2 different errors. But I think the important part here is what we see. Since we don't have p-values, that's why we're comparing it to the GLM. So if we look up here, so it looks like the z-value got was like -3. Just for reference, the intercept was not significant. It was like 0.96. So if we look down, even at our kind of best fit model here, the estimate now for treatment is 0.15, or even for this one here, yeah, it's 0.15. And even for like the robustity is only about 0.89, so that's lower than that intercept up there, which means after accounting for the structure, it doesn't look like there's any difference between the placebo and the drug. So that's the conclusion I would come to there. We've made it to our second assessment. Take some time to work on these, and then we'll step through them together. Okay then, so for one, if you want to have just a random intercept alone, you'd have 1 bar random. If you want slope and intercept, you'd use C. For this one, since we're using Poisson data that's non-normal, we want to use a generalized because it's not normally distributed. Of course, you could also use a generalized linear mixed model, because we can see here that there's a lot of overlap between a lot of these more advanced procedures. So then looking here to compare which one is a better effect or better fit, we look at the naive error and the robust error, and the closer they are, the better the fit. So exchangeable, actually, they're not very different at all, so this would be a better fit. And for 4, does it appear to be different across group and time? Yeah, I would say so, especially most notably, they all kind of start at the same time, but it looks like group D ends up having a lower percentage than either of them. Definitely looks like D and C look the most the same, and then kind of group B has this sharp increase. But looks like both time and group are different. Alrighty then, our last approach will be structural equation modeling. And really what it is, it's a form of multivariate statistical analysis. So you have can have more than one y variable, more than one x variable. And really it's a mashup of factor analysis with multiple regression analysis. And really it's used to impute relations between unobserved constructs, also known as latent variables, from observed variables. So that's what factor analysis does, is to try to like condense different, like say, predictor variables into like one or more like kind of super variable, like latent variable that you can't really measure but directly, but you can measure with other things. So like the idea here is I have this example. So and then where the multiple regression comes in is because you're trying to model certain things as a function of other things. But so this would be like an example of a structural equation model where the like intelligence would be like a latent variable. You can't really measure it directly, but you might have a bunch of scales that could maybe hopefully measure it. And then same thing with academic performance. And so you're trying to figure out relations between latent variables and observed variables. And so a general approach would be you specify your models, you estimate parameters, you assess how well the model fits, you change the model, and also a lot of times you're trying to build studies, so you might have sample size and power to figure out how many samples you need to get results, and then you also need to interpret things. So a lot of times you're actually a big part of this is actually building these sort of conceptual models. So in typical parlance, boxes will be these observed variables, stuff you can measure with the circles, or these unobserved or latent measurables. And then there'll be these different paths. So there'll be arrows from one thing pointing to another. So when they're pointing, it means like the first variable affects the seventh. So intelligence affects whatever the scale is here. And then if there's these small numbers here, typically if they're shown, that's the value of that path coefficient. So that's like a regression coefficient. And if there's no number, then that's estimated from the data. And then if there's curved double-headed paths, that's covariance. That isn't otherwise assumed. And I think, though, in these situations, these are another kind of double-headed error where it shows sort of the error for each of these. So we'll be using Stata because it has nice properties with it. And so there's two different formats you can use actually to create structural equation modelings in Stata. First one is a command line where you actually just type it in manually, but you also do it graphically. So these two are showing the same sort of thing here. We can see here you can build your observed variables, your latent variables, your interactions, like you see the double-sided arrow, the path arrow. And in the command line, you just do like, you typically, the setup is like L is for latent, M is for your measured, but it'll just depend on what these actually are. These are just dummy variable, placeholder names. So, for example, it doesn't really actually matter too much about spacing or setup or the direction of arrows. You can really have it set up any way you want. So for this one, it has L1, so that's creating this, having this, and then these two arrows show that this one is affecting these two. You could do it separately or in a different direction. So this line here, where you split them out, is actually the same as this line. So even though the direction of the arrows is different, it's indicating the same relationship. And even though it's individually or combined, it does the same thing. And if you want to do the covariance, those double-sided arrows, you have to do formats like this, where you have this E, and then like say, this one isn't shown here, so if we wanted to draw it, M1 and M2, it'd have to be like something like this. But then this one is how we created the arrow here. Okay, so we're going to be looking at three examples. First one is a pretty classic Whedon data, and then that's from this setup here from Stata, as well as this fictional data, and then this effective cognitive arousal data, also found in this Stata. Okay, here I am in Stata. So we'll take a look at the Whedon data set first. It's kind of a classical socioeconomic experiment. So there's a couple different ways we can go about this. I'll show you both. First, I'm going to open a script, also known in Stata as a do file. So this is one way we could set up our structural equation models by just plotting out things here. This gets our data out and then describes it. So we have it here. There are a bunch of different variables, and then we could kind of based on kind of this classic data, we can set up structural equation models kind of like we have here. But I actually want to show you another way too, is you can actually create a diagram and run it. So you can go down to SEM here, model fit and estimation, and actually pull up this builder. You can do things here. I already have something ready to go, so we'll take a look at it here. So here's that, and here's all built in. Let's just delete a couple things here just to see how it's done. So once again, the squares are observed variables. So if we want to pull in here, we just go over to that, add observed variable, and then we can click and edit it. And so our data is already loaded in, so we want to recreate what I deleted. So that's anomia 67. Then we want a latent variable, that's a circle. Once again, these aren't observed, so we'll have to kind of just create it and then name it ourselves. So let's do, once again, alien 67. And then we want to show paths, so we think that your alien path is here. It's going to be affect these two observed variables, and that obviously this is across time. So alienation 67 will probably affect alienation 71, and then we think social and economic status will affect that as well. Then to estimate this, we can just click here, run an estimate to do the default for now. It's actually going to populate the coefficients here, but then also back in Stata, this is our outcomes. So like our coefficients for those regressions, significance, and then the big thing here is we need to check our model fit. So that's this LR test of model fit versus saturated. So it tests our model we have here, and then a potentially saturated model where like it shows every single interaction. And if this is significant, which this means that we reject the null hypothesis that this model we have here is as good as a saturated model. So if this is significant, we need to modify our model. So then we can do that by checking what possible modification we want to do. So the best thing is to do these, look at these modification indices. So we're going to do that using this term here. And then it's going to show us all our possible things here. Let's look at the covariance, because we think maybe there's covariance going on. And some of the biggest ones that kind of stick out here and most logical would be, well, the covariance between anonymity in 67 and 71, as well as the powerlessness between 67 and 71. So let's try adding those to our model. And so this time, let's actually go and do it through the text. So here's our do file. This would just reproduce that model we had created by hand. But then this time is similar, everything else, but then we add these covariance structures. So covariance E, anomia 67, 71, powerlessness is 67, 71, and then so we have no log, just to make it a little less noisy. And then here is our output. Again, very similar, all of our coefficients, different structural, so these are our unobserved variables. And keep going. And then now what we see with our model fit here is that it's no longer significant, which says, hey, this is actually a pretty good model. So going back to here. And of course, if we wanted to do this by hand, we could have those covariances like, actually, whoops, we don't want that. We want to delete that. We want anonymity 67 and 71, and then powerlessness 67 and 70. That's how you do it by hand here. And so that is the first example. So let's go on to another example. Let's open up here. One. So this is just sort of a fictional example. Say we have 4 different measured variables, and we have one latent variable. That this would be a pretty simple setup. So let's try running that. Oh, so we see here the variables are not a data set. So remembering, we actually have to go to Stata. Let's open a different do file. So this is another example. We need to get our data in, summarize it, and do some notes. So let's run these here. So this is a fictional data set, different variables. And so we've seen the actual model. Let's close that. But now this is our model, but let's actually run it from the do file. So look at these side by side. We see that X, we think, affects X1, 2, 3, and 4. So we'll have it like that. And we'll just run that. So what that does here. And we can see that, this is a very simple model. Looks like these are significant, but then our chi-squared is actually set up, so this is a good enough model. Okay, finally, we're going to look at one last example. So I'll show you both the path diagram, so we got here, and also the do file, which has the scripts. So let's just run describe so we understand what's going on here. Okay, so this data has 10 different variables, A1 through A5, C1 through 5, and these are different measurements of affective arousal, 5 different kinds, and then 5 kinds of cognitive arousal. So the idea is to try to build a model like we saw here. Where we think that affective arousal affects these 5 different measurements, cognitive arousal affects these 5 different measurements, and then there's probably some sort of covariance between each other. So we could build this from scratch. Of course, though, we could also just run something simply like that. And you see here that in this line here, there isn't any covariance I have specified because, but that's assumed by the model because they're both latent variables here, that they assume that there's going to be a covariance. So let's just run this either way. It's going to pop out. So run it like this. Like I said, either way, it's going to spit it out on our model here in Stata. So we see a lot of things going on. As usual, our different coefficients, and looks like our fit of the model isn't very good because there's a lot of this is significant, so it means we can still add relationships. And another thing to see here is that some of these coefficients, like especially looking at variance, and or the covariance between the two of them, this number doesn't really make any sense. I don't even know what that means. So one thing we can do actually is standardize our variables by adding this SEM. When you run SEM, if you run standardize, we'll actually standardize them. So then these are set to 1. So then these are essentially, these coefficients are essentially like covariance, or sorry, not covariance, correlation. So you see like that, affective arousal is correlated to this A1 about 0.90. So this would be like an R value. And even more importantly, like for example, when we go down to a covariance between the two of them, we see that this number makes a lot more sense now that as a correlation. So they're pretty well correlated. But it's usually better than with correlation to also get like R squared. Instead of doing that manually, we can let our data do that. And so we can use this ESTAT QGOF. And then that gives us, so we see here, these are the different variables. We can see now that we can get the R squared here. So for example, A1, the R value or the correlation was 0.90. So taking that squared it explains almost or over 80% of the variation. So that's useful. Then what we can also do is, if we want to look at a little more in-depth goodness of fit, because we get that goodness of fit when we just run the SEM, but we can actually do this ESTAT goodness of fit stats all, which will give us everything. So including that likelihood ratio that we see at the bottom of our test, see that it's like model versus saturated, it's significant. but then we can get population area, AIC. This is good for like comparing different models, different comparisons. So that's useful. Finally, let's also look at running the modification indices again. But first, what we're going to do is actually run a structural equation model where we actually take out that covariance that we had. So if we really wanted to do this in here, we would just come over to this variance and delete it. But if we want to explicitly add that in just command line, we'd have our model like this. We've seen before, effective, cognitive, and we do covariance, effective times cognitive, and then this at 0. So like explicitly, otherwise it'll by default add it. So this will explicitly take it out. So let's run that, and then we'll run modification indices. Okay, so now this is our simpler model. We can see that chi-squared is a lot bigger, which means the simpler model without the covariance is less good of a fit. But then going down to the modification indices, we see that unsurprisingly, this covariance being ineffective and cognitive is quite large. So it would be a good idea to add those two there. And we can see if we were to move on and try to, add more paths to the model we had, we might want to look at, like for some of the highest ones are like some of the A's compared to each other. That might be a place, maybe some of these E's as well. But that would kind of take some work to do to work around and try to make a better model. And it also probably has to go into looking at, well, what are these variables measuring? Like, is there a logical reason behind, say, A1 being covariant with A2? Kind of depends on the actual measurement. So kind of the take home with structural equation modeling, it's actually surprisingly easy to build things, though it takes a lot more work to interpret how well they fit and to modify them. Alrighty, we've made it to assessment 3. Take some time to work on these yourself, and then we'll walk over them together. Alrighty, let's take a look at the answers here. For this diagram, B is latent because it's a circle, while E is observed because it's a square. For this, we'll use the asterisk between the two to get the covariance, and then the function COV. Looking at this fit, this is significantly small that its p-value is not significant, which means it's a good enough fit because there's no indication that adding more paths would improve the fit. And finally here, proper line path for the diagram to the right is going to be A because we have our latent, and then the arrow pointing this way means affects these two, and it doesn't matter the direction of the arrow, and you can do these two at the same time. Now that we've blustered our way through some examples, let's cover some caveats and concerns about this more advanced modeling. So the more complex your analyses are, of course, the more work you'll need to do for understanding. And in a lot of these examples, we really just scratch the surface. A lot of what's going to be your task when using these models is using a lot of multiple modeling. You'll try one, see how well it fits, try another, see how that fits, compare the two, tweak, check assumptions, try test, and over, so you really understand what the best model is and how it is explaining your data. Some more advanced data issues that you'll need to keep in mind as you do analyses. You might have to restructure or reformat your data, like going from wide data to long data. With longitudinal data we saw, you might have to restructure by including a nesting structure. And also another big thing in, say, longitudinal data is missing data. You might have to account for that or keep that in mind. And as we saw here, I actually showcased 3 different softwares. So you might need to use a different software to get the job done than you're possibly used to doing. Like here's an example of a very complicated structural equation modeling. If I wanted to replicate this, I'd probably use this in Stata so I could draw it out. As I see here, I did have to try to type on a command line in some sort of analog in R. That'd be a lot of pain. So you might have to broaden your statistical toolkit a bit to get things done. But in general, just realize that these complex analyses are like puzzle pieces that you have to fit together to hopefully at the end have a full picture of the system you're trying to model. So let's get into some real-world examples of some of the types of data we've used. So this is an example from ecology. It's on microbial feeding nematodes. This is a great example of more complicated random variables. This is actually what's called a strip split plot. They have 4 different treatments: nitrogen, carbon, phosphorus, and then combination of the 2. But then they also have mode and unmode, shown by clear or lines. And then finally with the red or the black, they have burned and unburned. So when you're creating a random statement in, say, SAS, you'd have to block it by which block of these 8 blocks it came from, which color, and then what shading, because they've randomized it to account for variation found across the landscape. Here's an example for longitudinal data, a pretty classic one. It's this doctor's study. They looked at doctors and smoking habits. And on the right here is actually data from the original paper, and they found that there was a very clear link between death from lung cancer and smoking. These are more modern graphs of them data, and that their survival curve of cigarette smokers is certainly lower than those who do not smoke. Finally, here's some structural equation models, both from Swartz et al., looking at data of cancer, both thyroid and colorectal cancer. We see in this leftmost structural equation model, there's actually no latent variables, but he's able to look at a multi-level modeling regardless. This one's a little more familiar to us. Given our examples, we have a couple latent variables, and then a variety of observed variables. Okay, to summarize, there's lots of advanced regression approaches. I hope this opened up the door a little bit to some of those. And really how you approach your data will really depend on what data you have and really what questions you're trying to ask. And the more complex, the more work, understanding, and patience you'll need to really reel in that data fish. And the good news is that our SAS data, really whatever you want to use, will have procedures for advanced approaches to help you on your way. Thank you for joining me for this. I am a member of DaCCoTA, and we are supported by the National Institute of General Medical Sciences. So if you did find this module or other modules we've done helpful, please reference us accordingly. Have a great day, and I look forward to seeing you next time on one of our future statistical modules.